to look at some different types of rational functions today and see what happens graphically when, for example, a non-permissible value cancels or the expression can be simplified. And how do we tell, for example, what the graph might look like if when we simplify the expression, the non-permissible value disappears, or what if there is a non-permissible value that is still clearly there once it's simplified? We're going to kind of explore that. Okay? So a point of discontinuity on a graph. A discontinuity on a graph is any time you have to lift your pen off the page to keep drawing the graph. Okay? So for example, in the rational expressions that we saw yesterday, the graphs were discontinuous at the vertical asymptotes. The vertical asymptotes, you would have to lift your pen off the page and then put it somewhere else to keep going. Okay? A point of discontinuity is essentially a hole in the graph. It's where there is just one coordinate point where it's discontinuous, but everywhere else the graph is continuous. So a point of discontinuity is a coordinate point on the graph where there's a hole. Okay, and it's actually called a hole. That's the name of this point of discontinuity. And it's essentially a point where the function is undefined. So to understand what this means, we're going to compare two functions. The first function is y equals x. Okay, so what does that look like? Yeah, it's a linear function that looks like that. Okay, no holes in that function. That function is defined everywhere. What about this? Okay. So firstly, if you were just looking at the expression x squared over x, could that be simplified? Yeah, we could simplify it to make it y equals x. Okay. This expression, though, has something that we need to consider, and that's a non-permissible value. In the original expression, there is a non-permissible value of 0. And so when we talked about in 20-1 rational expressions, we always said to you guys, you have to state the non-permissible values before you simplify. So this function is different than that one in that there's a non-permissible value of 0. Once we state that non-permissible, we can go ahead and simplify it and say, okay, well, this is going to actually be y equals x, with the exception that x cannot equal 0. Now, graphically, what will happen is there will be a hole in the graph at that point. Everything else is going to look the same. Whoops. Okay, I think my sleeve touched the smartboard briefly. Because the line went right through the hole. But everything else is going to look the same. Okay. Now, these holes in a rational expression, or rational function rather, only occur when one or more of the non-permissible values is canceled with a factor in the numerator. Okay, so when the rational function can be simplified by canceling common factors in the numerator and denominator, that could mean that one of the non-permissible values just sort of disappears once it's simplified. That's when you will see a hole. When something can't be canceled, right, then you're going to see a vertical asymptote. Okay, so after you simplify, if you can still clearly see that non-permissible value in the denominator, you'll have an asymptote. So we're going to look at a bunch of different types of questions to basically see how will this function behave graphically once we simplify these expressions. So here is one example. F of x equals x squared plus 2x minus 3 over x minus 1. Okay, so this is a rational function. It's a polynomial over a polynomial. What are the non-permissible values here? Right. X cannot equal 1. Okay. Now, the numerator is actually factorable. So if we factor the numerator, let's see, we were looking for two numbers that multiply to -3 and add to 2. So that would be, let's see, multiply to -3, add to 2, plus 3 minus 1. I'm getting distracted because I just heard my name mentioned across the hall, and I'm like, what are they saying over there? Okay, over x minus 1. Okay. So this can be simplified. We can cancel this factor of x minus 1, and this function, f of x equals x plus 3, along with this non-permissible, is equivalent to the original. Without the non-permissible, they're actually not equivalent by 1 point. Okay? But if we state the non-permissible as well, we can say that these two functions are equivalent. Okay? So in terms of graphing this, essentially what the graph will look like is it's going to look like this linear function, f of x equals x plus 3. However, when x equals 1, there will be a hole. Okay? So when x equals 1, if you put a 1 in there, the y value would be 4. So this is where the hole is going to occur. And otherwise, it just looks exactly the same as the linear function f of x equals x plus 3. Y-intercept of 3, slope of 1. Yes?
Sorry, why is it there?
Why is the hole there? Because really what we're graphing is the original function. In the original function, if you were to put a 1 in there, you'd get 0 in the denominator. Okay? All right. So in terms of analyzing the behavior near the non-permissible value, so let's talk about this. As x approaches 1 from the left and the right, what does y approach? If you get really, really close to 1 on this side, what is the y value getting closer to? 4. What about from this side? It's also 4. Yes. So as x approaches 1, y is approaching 4. Y is approaching a finite value. There isn't actually divergence when x gets really, really close to that non-permissible value. And if we compare that to asymptotes, there is divergence because they either go in opposite directions or, with the case of 1 over x squared, from both sides it approaches infinity, which is still not a defined value. Okay? Now, if you go on to take Math 31 or you look at calculus in university, this will be very, very significant. Okay? And this is actually called a limit. So what we're saying is, what is the limit of the function? What is the function approaching as x approaches 1? That is a finite value. So the limit as x approaches 1 is 4. Even though that point doesn't actually exist. A limit is not what is the function when x equals 1. It's what is the function close to as x approaches 1. Okay? This function has a limit of 4 when x approaches 1. Now, if you compare that to something with an asymptote, let's say we're looking at where is it? Oh, no, I'm going too far. This one, right? As x approaches 0 here, there is not convergence in the graph to a specific point. There is divergence. The y values go in opposite directions. Thank you. So this, we would say here that as x approaches 0, in this case, the limit doesn't exist, whereas with a hole it does. Okay? That's just a little bit of foreshadowing. Where was I here? Here I am. Thank you. Okay. So we're going to do a comparison here of a couple of different functions. Both rational. One of them is f of x equals x squared minus 3x over 2x plus 6. And this other one is g of x equals x squared plus 3x over 2x plus 6. Okay? So before we do anything, actually, before I look at non-permissible values, I tend to do this first. I factor everything first because, you know, typically your denominator might not be factored, and then it's harder to see what those non-permissible values are. Okay? So if I factor this function, in the numerator, I have a common factor of x. And in the denominator, I have a common factor of 2. Okay? What's the non-permissible here? Ooh, x cannot be plus or minus 3. Okay, so let's say x was 0. This would be 0 times negative 3, that's 0, over 2 times 3, 0 over 6. Is that defined? 0 divided by 6. Yeah, 0 divided by 6 is 0. So actually with these expressions, it is totally fine for the numerators to be 0. We just can't have a denominator of 0. 0 divided by any amount is still 0, right? If you have 0 cookies and you're distributing them amongst 10 people, each person gets 0 cookies, okay? But we can't have an x value of negative 3 because then we would be dividing by 0. The only time that we consider the factors in the numerator is if we're actually dividing by that rational expression, because then we'd multiply by the reciprocal and the numerator and denominator would switch. Okay. All right, so does anything cancel here? Does anything cancel? No. Okay, so what we can tell from that, if nothing cancels, we know that there is going to be a vertical asymptote at x equals negative 3. Okay, so I'm going to put that in here. Okay, now graphing this particular rational expression function is way beyond the scope of this course because it is not, we can't look at it through the lens of transformations. Okay, when you do some calculus, you could graph this by hand without the use of technology, but not in this course. So at this point, we're just going to use technology to graph it. Yes? You're good? Okay. So what does this look like? All that we could say is that there's a vertical asymptote there, but nothing else. Whoops. Okay, so I'm going to graph, let's see, x squared minus 3x divided by 2x plus 6. Okay, and I'm going to go zoom standard. I'm going to change my window settings so we can see a little bit more here. Let's see, let's make this negative 25. Okay. So this is actually really interesting. Technically, this graph has 2 asymptotes. It's got a vertical asymptote, and it also has slanted asymptote. Okay? So look, all we care about here is the vertical one. But if if you learn more math, then you'll see why. It's actually pretty cool. You can look at the equation and figure out why you have that slanted asymptote. But where was it? I can't remember what it looks like. Okay, so I just want to sort of get a rough idea, like, okay, so here is the x-intercept and the y-intercept, and here's the other one. So, you know, there's a point here and here, and it kind of goes like that. And then this one is kind of going the other way, roughly. Yeah, and technically there's a slanted asymptote along there. Yes? No, the only ones that I really care about in this course are the vertical ones. Yeah, so I could ask you, what's the vertical asymptote here? And by factoring the function and seeing, oh, that x plus 3 doesn't end up simplifying, you should be able to predict that there is a vertical asymptote at x equals negative 3. But beyond that, the expectation is that you're using technology. Okay? Now, compared to this function, if we factor g of x, then there's a GCF of x in the numerator, and we're left with x plus 3. And in the denominator, there's a GCF of 2. Okay, so there's g of x. What's the non-permissible value here? Yeah, still same thing, right? X cannot equal negative 3. However, this one does simplify. It simplifies to x over 2, or 1/2 x. So this one is going to look linear, except that there will be a hole when x equals negative 3. Okay? So if you think about this in slope-intercept form, right, 1/2 x, well, the y-intercept is 0, and then you go up 1, right 2, up 1, right 2, up 1, right 2, down 1, left 2, down 1, left 2. Now here you got to be careful. This is where the hole is. Okay? On your calculators, that hole isn't going to actually look like a hole. It'll look like there's a line there, because remember that on either side, you can get infinitely close to negative 3. And so that infinitely close piece, like your eye can't distinguish the fact that there's no point there. Okay? But when we're graphing these by hand, we want to clearly show that there is a hole in the graph. Okay? All right. So the last thing we're going to do today is a little bit of matching. So what we want to do is be able to look at these functions and without technology, be able to match one function to its graph. Okay? So where do you think we could start here? Factor everything. Yes. Okay, so if I look at a of x, can I factor the numerator? No. Can I factor the denominator? Yes. I'm looking for two numbers that multiply negative 2, add to negative 1. That's negative 2 and 1. Okay, let's look at this next one. Okay, so can I factor, well, the numerator is already factored. There's nothing to do there. Can I factor the denominator? Yeah. It's a difference of squares. Okay, so actually, if I state non-permissible values, I can simplify here. Okay, so the non-permissible values are plus or minus 1. But now I can simplify. If I cancel this in the numerator, I'm just left with 1. So this one's going to look like 1 over x plus 1. with those non-permissibles. So let me ask you something. In that function, are you going to see an asymptote? Yeah, where will the asymptote be? Almost. -1, right? Because this factor didn't cancel. So there's going to be a vertical asymptote at x equals -1. What about when x equals 1? There's going to be a hole. That's right. Okay, so the factor that canceled, that's where the hole will be at that non-permissible. If one factor doesn't cancel, you're still going to get a vertical asymptote there. Okay, so when I'm looking at this, you know, and before I even look at the graph, what I can see there is that I'm going to have two vertical asymptotes. One when x equals when x equals 2 rather, and one when x equals -1, because nothing cancels here. So I'm going to have a vertical asymptote for A at x equals 2 and -1. For B, I'm going to have a vertical asymptote at x equals -1, and I'm going to have a hole at x equals 1, because that was the factor that canceled. Okay. C of x. So I can factor this one as well. Two numbers that multiply to 6 and add to -5. So that's -2 and -3. Okay, so this is over 3 minus x. Could I cancel 3 minus x with anything in the numerator? Yeah? Well, I have to do something first. Yeah, take out the negative. If you take out the negative, then this becomes -3, that becomes positive x. Right? And if you were to put this back in, you'd end up with x minus 3 or -3 plus x, right? Which is the same thing. So now that I take out that negative sign, yes, there's a factor that will cancel. However, I have to also think about non-permissibles. So what's the non-permissible value here? 3. Now that's the factor that cancels. So we're going to see a hole. At x equals 3. Okay? Now this is going to simplify C of x. Will simplify to x minus 2 over -x. No, sorry, -1, right? The negative sign is still there. Now in terms of thinking about slope-intercept form, because that's typically the easiest way to connect a linear function to its graph, think about this being x over -1 minus 2 over -1. Right? X over -1 is -x, and then this becomes plus 2. And so you're going to have a linear function with a slope of -1 and a y-intercept of 2. And we're also looking for a hole at x equals 3. Okay, so let's see. Here I need two vertical asymptotes at 2 and -1. That's right here. Okay, so this is A of x. Here I'm looking for one vertical asymptote and one hole. Vertical asymptote's when x equals -1. Hole is when x equals 1. So this is B of x. Okay, and finally, C of x, I just have a hole.
Can you go back to the fitness center so we know about it? Back to the fitness center.
And I have a hole when x equals 3. Okay, so this is C of x. Okay, now I actually think a more interesting question would to give you guys 3 rational functions that look exactly the same, but have holes in different places, right? Because then you really got to know your stuff. All right. Does anyone have any questions? Yes.
How do we determine when something is an asymptote and when something
Okay.
is a
Good question. So When you will get a hole is when the factor that produces a specific non-permissible value cancels. Yeah, right? So a hole is when a factor in the denominator cancels. And essentially what you would see is that when simplified, that factor just disappears. In the simplified version, you don't really see that non-permissible. Okay?
Valerie,
An
back key to
asymptote
the main office, please. Valerie, back key to the main office. Thank you.
is when, after simplification, you still see that factor in the denominator. Okay, so let's see. For example, okay. Say I have f of x equals x cubed minus 4x over 3x squared plus 6x. Okay. Now if I factor the numerator, I'm going to do one little piece of factoring just above so that I don't have to write it a million times, but this has a GCF of x, so I can take an x out here and I'm left with x squared minus 4. Okay. And the x squared minus 4 is a difference of squares. So actually in the numerator, there are 3 different factors. Okay. In the denominator, I have this GCF of 3x. Okay. So looking at factored form, will there be any asymptotes on this graph? No, because both of the factors in the denominator that will produce a non-permissible value can be canceled with a factor in the numerator. So we're not going to have any vertical asymptotes here. What we will have are 2 holes. Okay, so as soon as well, actually, first I should say x cannot equal 0 and -2. Okay, so those are the non-permissibles. But when I simplify this, what I end up with is that along with these 2 non-permissibles, f of x essentially equals x minus 2 over 3. Okay, so if the simplified version does not contain those initial non-permissible values, that's when you're going to see a hole. Okay, but if you simplify and you can still see why that non-permissible value is there, even after simplification, that will be a vertical asymptote. Yes?
And could you further simplify that so the x over 3 minus 2 over 3?
Yeah, so the question was, could you further simplify that to make it x over 3 minus 2 over 3? So I wouldn't say that that's necessarily further simplification. What I would say is that's a manipulation that I would personally do to help me graph it. Because then I can clearly see, okay, here's the slope, it's 1/3, and here's the y-intercept, it's -2/3. Yeah, but if I didn't ask you to graph it, then you could just leave it like this, right? Yeah, so good question, and that's sort of where we get to the point in math where there's not really a black and white answer. It's more like, what do you want to do with it? Right? If you want to graph it, yeah, it would be helpful to put it into slope-intercept form. But if not, you can just leave it like that. Yeah. Okay. All right. Any other questions? Okay. So I'm going to stop there for today.